Okay, let's move on to mass. What about mass? Mass in special relativity. Well, what is that? Well, the big problem, again, always the big problem in all of mathematical physics, specifically you could say in special relativity, is that there are no definitions. There are no definitions. And so they get away with murder because they say, well, time, we don't really know what time is. Energy, well, we don't know what energy is. They don't know what anything is. They don't know what mass is. They have like 7 different definitions according to the Wikipedia. So they have all these words. They don't have a definition for any of them. And with those words, they're going to use them to make their case. And so they're talking about X's and Y's. What's X? Oh, I don't know. What's Y? I don't know. But let me tell you, the X moves this way and the Y went that way. And what are they talking about? So this is where the problem is. The problem is these people have not defined the words with which they make their cases. They all remain undefined. And there's a reason for that as well. And the reason is that, they can't define them because they're concepts and they're going to be using them as objects, as things. They're going to move them around. They're going to bend time. They're going to bend time. They're going to transfer the energy. They're going to vibrate the field. And so if they define it as a thing, fine, they can do that, but these are not things, these are numbers. And so they have to use them as numbers, and then they say, well, but I can't use them as physical objects. So they cheat, and they cross the line, bringing all their words into physics. That's where the problem is, okay? And so here, mass, where the problem is, summary of mass is a question of definitions, okay? What is mass? Well, Newton essentially defined it as quantity of matter. And we all understand that. I mean, we can picture it. We can we can get an idea of what he's talking about when he says quantity of matter. We don't have a unit of matter, but we can say, okay, there's so much matter. Let's assume, like we do in the rope model, that the atom, the hydrogen atom, is the unit of mass. Okay. So all you have to do is count the number of hydrogen atoms. And you count a big atom like uranium, 92 protons, 92 atoms, 92 hydrogen atoms, plus, 200 plus 218, I think it is, neutrons. So you count every one of those as a hydrogen atom. And all you do is just add it up. It's 140 some neutrons, and the total comes up to 200 plus 218, I think, units, which would be 218 hydrogen atoms. So you would consider this a big atom. That's all it is, a bunch of hydrogen atoms. That's all the uranium atom is. And so if you look at it that way, you can say, okay, what's the unit of mass, the hydrogen atom? How many units of mass does this object have? 1 trillion. And then you have the quantity of matter. What do we do with quantity of matter? We count them. We count every atom in there and say this object has exactly 1 trillion atoms. That's the mass of that atom, of that object. Okay, it's got 1 trillion hydrogen atoms. That's the quantity of matter version. Okay. What they had to do, since they measure everything instead of counting, because they can't count atoms, right? So they said, okay, we're going to measure. And so they started measuring. And that's where they got confused, because then they mixed mass with weight. Okay? And they say, well, how do you measure mass? Well, we weigh it and we put it on a scale and measure. How much does that thing weigh? Well, again, we put it on a scale and measure it. So we talk about kilograms for both, for mass and for weight. Kilograms should be used really only for weight and not for mass. Mass should be counting. You should count atoms. You should give me a number in terms of atoms. That's the way it should work. And that's not what we do. We measure by weighing. That's how we determine mass. Okay, so what's the problem? The problem is that they invented this thing called rest mass. And they use the word rest mass. People say, oh, what could they be talking about? Well, I'll tell you what they're talking about. They're talking about quantity of matter, because when the thing is at rest, it's not moving, so we don't have any motion. We don't have any momentum. We don't have any, acceleration, any velocity. It's standing still. What are we talking about? Quantity of matter. So rest mass is quantity of matter. Why don't they call it quantity of matter? Because it's better to say rest mass, because they're going to contrast it with the next one, relativistic mass. What is relativistic mass? Weight. That's what it is. Because now they're talking about the force the thing, whatever you're measuring there, the force it applies, the pressure applies on a scale. That's what they're doing, okay? And the funny thing about that is that, yeah, you can only do that because when they talk about relativistic mass, they're going to introduce the speed of light. They're saying, well, the mass changes as the closer you get to the speed of light. And what do we mean by that? Well, we mean you're pressing down on a scale. But see, you can only travel at the speed of light, not here on Earth. It's got to be out there in the cosmos. So the scenario is always a cosmic scenario where you see a rocket or a ball or whatever you want to see, a ruler, right? And it moves at close to the speed of light. And then they say, well, it weighs more, it's thinner, it shrunk. And you get into these time evaluations. What are we talking about? Well, we're talking about how it approaches an object, a celestial object, and that's known as gravity. And the funny thing about that is that special relativity is a gravity-less theory. There is no gravity in special relativity. Why? Because it's flatland. It's you can't fall down in flatland. There's no gravity in flatland, and that's the issue with this relativistic mass. They're doing it in a context of gravity, so they have a contradiction, a fundamental contradiction, because the only way an object can speed at the speed of light towards, for example, a star or a planet is in the cosmic scenario. It's got to be out there. It can't be here on Earth. There's no special relativity here on Earth. The special relativity is out there in space. And so if the object is falling towards the sun, that's gravity. And special relativity says we don't do gravity. It's a gravity-less scenario. So you try to explain that. They have a fundamental contradiction. Okay, so what's the issue? The issue is that if the number of atoms, right, goes up, then you have more atoms. In other words, if this thing, because of speed or because of whatever, increases its mass, then what we're saying is it acquired more atoms. That's what we're saying, okay? There's no such thing as pressure in this case. We're not talking about pressure. We're saying we have more atoms. The thing has become more, acquired more atoms, okay? That's the notion of quantity of matter. But if you're talking about speed, then you're talking about weight. You're talking on how much it presses down upon the scale. And on the cosmic scenario, the only way you can visualize that is it approaching a star or a planet, gravity. Okay? So proper mass doesn't change. In other words, if the special relativistic notion is that if the thing is traveling with you, it doesn't change its mass. It only changes for the observer who is measuring you from far away. For them, they measure something different. Who cares? What's that got to do with science? What's that got to do with physics? So he measures something different. Well, he's wrong, because whatever he measures, whether more or less, it doesn't really affect the object itself. The object, obviously, in its proper frame of reference, has a certain weight, certain mass, right? Actually, weight, because that's how we measure mass. We weigh it. And so it's got a certain weight locally. And those are the number of atoms that thing has. You have a ball, a bowling ball maybe. It's got all these atoms in there. And whatever atoms it's got, it doesn't change. And if it's in the local frame, it weighs whatever it weighs, 2 pounds, 3 pounds, whatever. From far away, you can say, well, it weighs more because you're traveling at the speed of light. Well, it weighs for you, but the ball only has so much matter in it. So they have a problem because they're talking about weight, but they call it mass. And that's when they get confused. Language is a problem. And again, weight just means bigger pressure on the scale. That's all it means. So, and that's what they're talking about. They're not talking about relativistic mass. They're talking about weight. Why they invented this term special relativistic mass, I have no idea. They could have stayed with weight and we were done. Okay, so here we have a scenario. We have this rocket, okay, and it's flying through the from one star to another. And it gets bigger because, mass increases, right? And here you see it, okay? So it's getting bigger because it's approaching the other star. Is that true? It's going on the speed of light, right? Or almost the speed of light, this rocket. And what they're saying, no, the rocket does not get bigger. What happens is the observer there, he's measuring a greater mass. But he's saying that the object in its local frame has not changed its mass. So what are they talking about? I mean, either it changed its mass or it didn't. And they're saying it didn't, but the guy measures it as if it did. And so what does that have to do with physics, with reality, with what's actually out there? Okay, the number of atoms has not increased in a single frame of that Universal movie. Whether the observer measured something different, well, that's his problem. He's got to go to a psychiatrist. His readings are off. He's got to measure the exact number of atoms that thing had, no matter where, in any frame of the Universal movie. Okay? So here we have two elephants, okay? And they're going to fall towards different suns. One falls to a small star, the other one falls to a big star, right? Well, the guy on the right is going to fall faster, okay? Because there's greater gravity in the one on the guy on the right. Okay, and so this is the issue that at a given distance from the surfaces of these two stars, okay, they both have the same rest mass, which is 5 tons, which is the number of atoms comprising each elephant. It's exactly the same. Okay, and in any frame of the film in which they fall, those elephants do not shrink. They don't get bigger. They don't get fatter. They don't get slimmer. They always have the same number of atoms. Speed has nothing to do with the number of atoms they're made of, and that's what rest mass is. But as they fall, what changes is what? Weight. That's what changes. And so this is where the problem is. They call that relativistic mass when they should simply call it weight, because they're just falling towards, a star. And we call that weight, right? You fall towards the Earth. Why? Because of gravity. What is that? That's called weight. Okay, so I'm sorry to tell you, that there is no such thing as relativistic mass. It's just weight. And here we see what happens in each frame of the film. Okay, what you have is the elephants start out, they both have 5 tons no matter what in each frame of the film. By 5 tons, I mean that the number of atoms has not changed. What has changed is the weight, right? As the elephants occupy different locations with respect to their stars, they're going to have different weights. So the 5 tons, meaning the rest mass, always remains the same. What changes is the weight all the way down. And so, try to tell that to a special relativist. He will not understand because he does everything with calculations. He doesn't have a visualization of what's happening there. He cannot make sense of it, right? He just makes sense of the math, but not of the physics of it. That's where the problem is. Okay, so here's why the elephants have a different weight. Okay, this is the rope model explanation, right? You can see that every atom of that elephant, here we only picked one atom in one of its toes, right? And you can see that those atoms are tied to every atom of the star that is attracting them. Okay, so you can see why they have different weights. They have different weights because the number of ropes converging upon that toe, that atom in the toe, right? One atom, right, is greater on the guy on the right than on the guy on the left. That's the only difference between this, okay? And yes, every atom in the universe is bound to every other atom in the universe. Bound, by bound, I mean it converts into an atom, which then converts again into a rope and so on down the line ad infinitum. Okay, so you can see why their weights are different. Okay? But the number of atoms in each elephant continues to be measured like 5 tons, meaning they're the same amount of atoms. Okay? They have the same number of atoms in both cases. Okay, so here we have 2 atoms so that you can see, because every atom has to be treated separately. Okay, here we have it. You have 2 atoms now. Okay? And you can see that if you do that with every atom in the elephant's body, you're going to have a big mess there of ropes. Okay? But every atom in the elephant is bound to every atom in the sun, in each one of those stars. And some people say, well, do the ropes go through each other? That's the one everybody asks. And they never ask the question they should be asking. See, and the question is, do neutrinos go through matter? Do fields go through fields? Do energies go through energies? Do masses go through mass? Is there a single space-time or many space-time? Are there many fields or just one field? And see, they treat them as concepts when they need to treat them as concepts, and they treat them as objects when they treat them as objects. And then they talk about superposition of particles in quantum mechanics. Nobody asks, well, does that mean that if there's a particle coming across and meets another particle and they superimpose and then they continue flowing, does that mean one went through the other? Yes, that's exactly what it means, but nobody asks the question. Everybody asks about the rope. How do the ropes go through each other? And the answer is all theories. There's not a single theory ever imagined by man where objects do not go through objects. Okay? And so if you have a theory that you believe, oh, my theory doesn't have that, I'm going to show you it does. So you better check your theories, because all theories implicitly have objects going through objects, electricity going through electricity, fields going through fields, waves going through waves. It's impossible not to do that. Okay? And so whatever you have as objects, as things, as mediators for light, gravity, etc., magnetism, whatever you propose, it's going right through something else. You can't avoid it. Okay? So think about that. So don't ask about the rope. Yeah, ropes go through ropes. They're always tight. Rope is always taut, right? It's always pulled taut. And ropes go through ropes, just like that. And you say, how can that possibly be? Yeah, that's the thing that kept everyone from understanding how our universe works all these thousands of years. Because nobody imagined that if an atom is bound to an atom, or like Professor Muller says from Berkeley, every atom in your body is being pulled by every atom on Earth, and every atom of your body is pulling on every atom of Earth. How do you pull if you don't have an elongated mediator between any two atoms of your body and every atom of the Earth? So yes, the issue is that no one ever pondered the possibility that in this invisible region, there are atoms connected to atoms through these elongated things that connect these atoms, that bind them or interconnect them, right? And nobody ever figured out that, yes, you can go right through with your hand, right through all these mediators. And nobody even pondered that. They say, no, there's nothing here. Yeah, there is something there. You just can't see it or touch it. Just like you can't see the air, you can't see the ropes, in this case, what we propose, that binds all atoms. Okay, so here we have another version of our elephants, okay? You can see what's happening there. As one elephant is falling towards its sun, you can see what's happening to the ropes. They're fanning out, and so the acceleration increases. And that's the acceleration of gravity there in a nutshell, in a picture. Okay? So it's easy to understand, no problem. You just have to go to, you see your shrink, right? About ropes going through ropes and things going through things. That's the only one that keeps everybody from understanding. From not understanding, I guess they understand it, but they don't. And they say, how can it go through rope? I cannot explain. That's magic. No, we have magic all around us. Quantum proposes magic. Relativity proposes magic. String theory proposes magic. They're all magic. They all go through each other. There's no such thing as not going through another object. Okay? And so you have to come to terms, and if you can't live with that, go see your shrink tomorrow morning. Okay, so here's God taking a picture of weight. Okay, weight has to be a static concept, right? What is that, 5 tons? Well, it's the number of atoms at a given location. At a given location. What is location? A static concept. Okay, we take a snapshot. We should be able to take a snapshot of weight. What is weight? Number of atoms from, in this case, one star connected to one atom in the elephant. That's called weight. That's the weight of that atom at that distance from that star. Okay, single frame in the universal movie. Okay, it's not a force, it's a tension. Okay, Newton put force there. No, there's no force. Why is there no force? Because it's not distance traveled. It's separation, fixed separation, distance of physics between, in this case, the elephant or one atom in the elephant and the surface of the star to which it's falling. Okay. What is weight? Number of effective ropes. The closer you get, the ropes fan out, you have more effective ropes. Okay. And the rest mass of the elephants have not changed, or of the star for that matter. Okay, it's just the quantity of atoms. So I think it's straightforward. The problem with special relativity is that they never define the word mass. They never will. They can't. They shouldn't, because if they do, their theory goes out the window. So they can't define it. They can't define field. They can't define energy. They won't, and they should not, because unless they want to destroy their theory. And so they use it as a concept, a mathematical concept over here, and then they use it as a physical object when they give you the physical interpretation. And that's where the falsehood occurs. Okay, that's when they lie or they fool themselves, whichever.